So our next common non-ferromagnesian silicate mineral is muscovite. Muscovite is a member of the mica family, which is those minerals that have that one plane of cleavage that peel off into the sheets. And you can see muscovite, like feldspar and quartz that we talked about already, has silica, has some potassium, aluminum. This is so it's called hydroxyl oxygen hydrogen, but no iron magnesium. Here is a picture of muscovite in its flat sheets. Now we're going to look at the ferromagnesian silicates, also known as the dark silicates. So these ferromagnesian silicates, they contain a relatively large amount of iron magnesium, and they're generally dark in color, which gives them the name the dark silicates. So our first ferromagnesian silicate is olivine, having iron and magnesium with silica. It is the most abundant mineral in Earth's mantle. It gets its name olivine because of its green color. Then we have hornblende. This is the most common mineral. I should say that olivine has the single tetrahedra structure. Hornblende has the double chain structure. And all ferromagnesian silicates with the double chain structure are called, it's called the amphibole group, and hornblende is the most common one in the amphibole group. See, it has iron, magnesium, and silica in it. It's very dark in color. Next is biotite. It's also mica, like muscovite, except it's ferromagnesian. It has iron and magnesium with the silica. It has that one plane of cleavage, so it's like muscovite, but just darker in color because of the iron and magnesium. Then augite. Augite is the most common mineral from the pyroxene group. The pyroxene group are all silicate minerals with the single chain structure. This is the dominant mineral in basalt, the primary rock of the sea floor. And see, it has iron, magnesium, and silica in it. So here's basalt that's forming from the cooling lava from Kilauea in Hawaii. And you can see how this basalt is dark in color. Why is it dark in color? Well, because augite is the dominant mineral in basalt, and augite is a ferromagnesian silicate. And whenever basalt cools, because of the structure of augite, the single chain structure, whenever it cools, it contracts, thermal contraction, and it actually cracks. The basalt cracks, just like mud cracks as it dries. But when it cracks into these column-like structures. So you can see this outcrop, where outcrop was bedrock intersects the surface of basalt. It's broken into these columns, okay, because of the reason it does this is because of the single silica structure of augite, the dominant mineral. And it looks like a fortified wall, also called a palisade. So that's why this rock unit, which is along the west bank of the Hudson River, gets the name the Palisades, if you ever heard of the Palisades. And so these are called columnar basalts, have this this feature because of the augite in them. So then we have the non-silicates. Okay, so the silicates are known as the rock-forming minerals because rocks are composed mostly of silicate minerals. Non-silicates, on the other hand, are known as the economic minerals because they have most economic purposes or uses. So you have the carbonates. That's anything that's bonded with the carbonate radical, calcium, one carbon and 3 oxygens. So that's calcite. That's just made to make cement and lime, or dolomite. Same thing, cement and lime. You have the halides, anything bonded with chlorine, fluorine, or bromine, like halite. It's common salt. Oxides, just bonded with oxygen. So hematite. That's an ore of iron. So that's how we smelt this to extract the iron from it to make steel. Magnetite, another iron ore. Corundum, aluminum oxide. This is a gemstone, also known as a sapphire. And then ice. We have sulfides, that was bonded with sulfur, so lead sulfides, an ore of lead. We extract lead from it. We have an ore of zinc, pyrite, and then we have a copper ore, and then a mercury ore, the sulfides, and the sulfates, those bonded with sulfur, sorry, and oxygen. We have gypsum, it's used to make plaster, and then we have the native elements. Those elements are just found in clumps by themselves, not bonded with other stuff, just bonded with themselves. So you have gold, copper, diamond, which is pure carbon, sulfur, graphite, also pure carbon, silver, and platinum. So the uses of these native elements is for commercial use in jewelry, but also for electronics, for pencil lead, and for silverware, and the platinum is used as a catalyst, and also for jewelry. And so, looking at a breakdown of the minerals in Earth's crust, the silicate minerals are the most abundant. Okay, so these are all silicas, right? Only 8% of minerals in the crust are non-silicates, those economic minerals. And of the silicate minerals, the non-ferromagnesian, the light silicates, are the most common in Earth's crust. Okay, so you have plagioclase feldspar and potassium feldspar. So the feldspars are the most common mineral group. And you have quartz, the pyroxenes, that's a ferromagnesian silicate, amphiboles, ferromagnesian silicates, and micas, which include both muscovite and biotite, and clays, and then all other silicates. So as you see, 39 plus 12, that gives us 51, and then plus another 12, 63% of all minerals in the crust are non-ferromagnesian silicates, and much smaller are ferromagnesian silicates. If you go into the mantle, the opposite is true. It's overwhelmingly ferromagnesian silicates and very few non-ferromagnesian silicates. So that's all for our lecture on minerals. If you have any questions, please don't hesitate to send me an email. I know I go through the lectures a little bit quicker. I'm just recording them because I'm not answering questions from the students in real time and so forth. So I understand it might seem a little fast, but you can rewind and listen to it, different parts of it if need be. And please, please, please send me an email or write down questions to bring to class. And I look forward to answering any questions that you may have.